Now let's try this problem of your textbook problem number 43, which says that a spring is fixed at the bottom end of a plane. This is the spring, right? And the plane has an inclination of 37 degrees. So a small block of mass 2 kg starts slipping down the incline from a dip point of 4.8 meter away. That means from here, distance is 4.8 meter. The block compresses the spring by 20 centimeter. That means 0.2 meter. That means when the block hits the spring becomes compressed and another 2.2 meter movement occurs. That means when this block slips downward, it moves 4.8 meter plus 2 meter. That means this total movement of the block is 5 meter and stops momentarily. Of course, when the block will hit the spring, it will stop momentarily. And then what will happen? The spring will bounce back. And then the spring rebounds back to a distance of 1 meter of the incline. That means thereafter, from here, the body once again travels by 1 meter. So the 1 meter traveling happens afterwards. First thing what happens, the block moves 4.8 meter, hits the spring and then moves another 0.2 meter. So total 5.8 meter, the block moves. So once again, we have to draw the free body diagram of this block. And what you find that the mg force of the block will of course work vertically downward. And the component normal to the slope is mg cos theta. This we have seen number of times, so now students. So if this normal force is mg psi cos theta, so then reaction force will be R equal to mg cos theta. M theta. And this mg will have a component along the slope downward, which is mg sine theta. Force mg sine theta will push the block downward. And there is one more force, let's not forget. There is one more force is Fs, which is frictional force, because here there is a talk of friction. The incline is not frictionless. In that case, it is mentioned that the incline is smooth. Well, now we start solving the problem. We find R equal to cos theta, which is equal to M is given 2 kg, G we consider 10, and cos of 37 degree. Well, on one thing, this 37 degree appears repeatedly. So you may always remember that sine 37 degree is equal to 0.6. It is better to try to remember this. Cos 37 is equal to 0.8 and tan 37 equal to 0.75. Since these are round figures, that's why you will find 37 degree in your numerical problems very often. Very often you will find 37 degree. Okay, this is cos 37 degree. This is equal to 2 into 10 into cos 37 is 0.8. 0.8 is 16. If you want to write the unit, one thing more we know, since we know R, we now know Fs. Fs, frictional force, is equal to mu R is equal to 6, because R is 16. Fine. Now let us consider downward motion. Consider downward, downward of a block. Next, we shall consider what happens when it moves upward. During the downward motion, what is the total displacement of the body? The law 0.8 plus 0.2 is equal to 5 meter. Total displacement of the block is 5 meter. And in that case, what is the work done by the body? Total displacement of the block is 5 meter. And in that case, what is the upward force? What is the downward force? Is mg sine theta. So we can write mg sine theta minus what is the upward force? Fs. What is the upward force? Fs. So this is the force. And how much distance does it travel? It travels 5 meter. It travels 5 meter. So this is the work done by the, this is the work done by the gravity. And this work is opposed by compression of the spring by 0.2 meter, right? So work done by gravity is this much, and this is equal to mg sine theta is 2 into 10. Sine theta is 0.6, 0.6 minus Fs is 16 mu minus Fs is minus Fs is 16 mu. This whole thing multiplied by 5 is equal to 2 into 10 into 0.6 is equal to 12 minus 16 mu multiplied by 5. So this is equal to 60 minus 80 mu. This is the work done by the gravity. And what is the work done by the spring? Work done, now we will do one thing. Work done by the spring, now we come here. Work done by rather we should write work done not by the on the spring. done on the spring is equal to half spring constant K x square. This is a general equation. Here, this is equal to K by 2 and x is 0.2, the compression of the spring, 0.2 whole square. This is equal to 0.4, 0.04 by 2, that is equal to 0.02. Now, this is the work done by the gravity, and this is the work done on the spring. And these two are same. So we write, therefore, and write that minus 80K, T minus 80K is equal to 0.02K. From here, this is one equation. 60 minus 80 mu. I am sorry. 60 minus K. That would have been a great mistake. 60 minus 80 mu is equal to 0.02 K. Right? Now let us consider the upward motion. Now we consider the upward motion. What happens? Spring does the same amount of work to bounce back by 0.2 meter. In the upward motion, the work done by the spring, because this time the work is done by the spring. Work done by the spring will be the same thing, half kx square equal to 0.02 k. And this work is done against the gravity. So we can write what is the work done against gravity? Or done gravity. Now we know the body is thrown back by 1 meter. It came down by 5 meters, but it is thrown back by 1 meter. And thrown back against the frictional force, same frictional force, Fs, because when the body is moving down, the frictional force moves upward. And when the body moves upward, frictional force acts down. So it is the same frictional force. So work done against gravity, work done by the spring, we have found this, and works done against gravity, I write against gravity by the friction. By the friction, that would be more clear. By the friction is frictional force is 16 mu that we have seen earlier. 16 mu into, it has gone up by 1 meter. So it is 16 mu Newton. Right? This is the work done against gravity by the friction. And how much potential energy, gravitational potential energy gained by the body? So we can write this way, potential energy gained by the body equal to nt sine theta, that is the component of mg in the direction of the incline into 1. This is equal to 2 into 10 into 1 into sine theta is 0.6 This is equal to 12 Newton. Right? Now, see, while going upward, potential energy gained by the body is 12 Newton. Right? Work was done by the spring. Who did the work? Work was done by the spring is 0.02 K, right? And this work has resulted into a potential energy gain of 12 Newton plus work against the gravitation of 16 Newton. That means this 0.02 K is equal to 16 mu plus 12 N. So therefore you can write, now we do one thing, we come here. Let us draw a division line here that there is no mix-up in the solution. So therefore, we write that 0.02 K, so 0.02 K is equal to 16 mu plus 12, right? And here found that here we have found, we have now two equations, I will show you. And we find 0.02 K is equal to 60 minus 80 mu. And here we find the same 0.02 K is 16 mu plus 12. So these two are same. Therefore, so now from here we go to, therefore we write 60 minus 80 mu equal to 16 mu plus 12 equal to 16 mu plus 12. From here we find therefore 96 mu comes to the left right hand side. So 96 mu equal to 60 minus 12 is equal to 48. So from here we find mu is equal to 48 by 96, which is 0.5. This is one answer. Mu equal to 5, which was wanted. Now just put the value of mu in any one of these equations. You will find the value of K. Let us say we use this equation now. So we have 60 minus 80 is 0.5. 0.5. This is equal to 0.02 K. Or what we find? 0.02 K is equal to 60 minus 40 is equal to 20. Therefore, K is equal to 20 divided by 0.02, which comes out to be 1000. So, this is another answer. Unit of K, you know, it is Newton per meter. And this is mu, which is unitless. So, this was the solution of this particular question. Next, we shall take another question of similar type of the same chapter, few minutes later.